Hi, Jeff Disher here again. Today I'm going to talk about sort of a kind of a very old question actually that we've kind of all asked from one point or another. What is a crash when it comes to a computer crash or a computer program crash, and why does it happen? Is there any way around this in general? So first of all, I'm going to talk through what a crash is in the sense of how does it differ from a freeze or an exception, just some kind of basic terminology. Then I'm going to talk about state machines as this is sort of a way that you describe in sort of a diagram, sort of what a program is actually doing and how you can tell that it's correct, and technically what a crash actually shows up as in that sort of diagram and why it's there. Now, is there any way to avoid a crash? And if there is, how would you do that, and would you actually want to? And are there any security concerns that come along with the ideas of crashes, specifically avoiding crashes? And okay, if we're being wary of trying to avoid crashes, is there any way to force one? And why would we want to do that? And how would that help us? And finally, I'm going to finish off with a little bit of a talk over formal verification, which is sort of a concept in computer science where you can mathematically prove that an algorithm is correct. So, first of all, crash, freeze, or exception. Well, a crash, this means that you got an unexpected or incorrect action that was requested of the program. So it didn't know how to handle the thing that was asked of it because of either it doesn't know how to handle that kind of input at all, or it wasn't ready for that kind of input at this point in time. So it doesn't know what it should do when it sees that, when it's in a particular state. Now, a freeze is, of course, totally different. It's when you're waiting for an action which never comes. Like you're trying to, I don't know, read a file over the network or something, and whatever's trying to read it is waiting to load all the data before it'll proceed. Well, if the network's really slow, it's going to seem like it froze. It might just be really slow. It's actually interesting. You can't prove in general whether a program that seems to be frozen is ever going to come back or not. Usually they're just being really slow, but sometimes they might be gone forever. And then there's something called an exception, often reported as an unhandled exception, and this is the same as a crash. Basically, it just means there was an exceptional circumstance which arose, and the program did not know how to handle it. So it's a slightly more worded out way of saying the same thing. Crash is just kind of an old, non-technical way of describing it, but they both mean the same thing. So crash itself is when the operating system or a virtual machine terminates a program when it does something that's invalid. Now, what's interesting about this is the program itself, the operating system or the VM doesn't actually know what your program does. It doesn't know if it's doing it correctly or not. But every once in a while, the program, if it's done something really bad, like if it's really gone off the rails, it'll do something the operating system can notice. Usually this is because it asks for something, it tries to use something it didn't request, because normally it's going to ask for things like memory and stuff like that as it's running. And then at some point it might try and use something like memory that it hasn't asked for. And so the operating system is going to say, okay, now I know that you don't know what you're talking about. So I'm just going to stop you right there. So that's what a crash ends up actually being. It's when kind of that external mediating entity actually has a way of noticing what's wrong. But because there could be a long wait between the point where you actually have the bug and when you actually see the crash, it's often hard to find the actual causes of this. So a state machine is a way that you can actually describe an algorithm in a computer, or even a process that humans are performing too. There's nothing necessarily computer related about this. So it's just a diagram of how to show this. Now, I've talked about this a bit in greater detail in some past videos, so I'm just going to quickly run through this as a way of describing correctness or incorrectness of a program. So in this case, we've got this kind of state machine. You can see the ovals are the states. The arrows are labeled with inputs that move from one state to another on that input. The double oval is what we refer to as the terminal state, a valid state you can end in, and the program will be correct. So what this state machine does is it can read sequences of input that have any number of AB pairs, at least one of them, followed by a C. So this, of course, is just a very simplified way of describing any sequence of operations you'd be performing this way. We'll just call them A, B, and C to make it simple. So, for example, a sequence like A, B, C will show up like this. We first start in the start state, where you always do. Then we get an A, so we go follow that arrow to the A state. Then we see a B, so we follow this other arrow to the B state. We see another A, so we follow it back to the A state. See another B, follow it to the B state again, and now we see a C, so we go to the C state, And now because we're done with everything, we can actually go into the end state. Now usually you'd actually draw this with the C being the end, but I just sort of stretched it out to make it a bit easier to see. So an example of incorrect input and what that would actually do looks like this. So we start at the start, we read the A, that tells us, okay, we go into the A state. Then we read another A and say, okay, wait, there is no arrow leading from this state when we have input A. So what happens in a state machine is anytime you need to handle some input and you don't have any way of handling that from your current state, that's when you go into what's just called the crash state. So this is what it means for a program to crash when looking at it in sort of a technical way through this sort of diagram. And this is also why it kind of tells you a little bit about how you can't necessarily recover from these because you might not know why you're there or what to do about it. So how do we avoid a crash though? If we can think about it as something that we don't want, okay, how do we make sure this doesn't happen? Is there any way that in general we can just not crash? And the short answer is no. There's sort of a bunch of different ways of looking at it or kind of tweaking your understanding of what a crash is so that you can get rid of some of the cases, but in general you can't avoid this because it literally means doing something you don't know how to do. No amount of policy fixes that. So one of the questions a lot of people ask is why not just do nothing? If something unexpected happens, why not just kind of ignore it and just keep doing whatever we were doing? Well, what does nothing mean? Right? Because like in that last example, if we just decided not to go from state A, we're just ignoring data and hopefully the next thing that comes by makes sense. Like, what does it mean to do nothing? Because doing nothing is actually doing a lot of something. It's making a very strong statement about what you're actually going to do. So you can't just avoid this by saying, let's just do nothing. And this is something that a lot of people kind of take this approach, even computer software developers. We'll kind of hope that this will work because it really sounds like it'd be nice to be able to just do nothing. And they eventually realize, no, you can't do this. So for example, what happens if you're failing to save a file? You've got something like a really important document, you're trying to save it out, and you've just made a small modification to it, but there was something wrong with your modification, or there's a bug in the program basically where it doesn't know how to handle this kind of modification properly. So you try and save it. And okay, it now suddenly realizes there's something wrong. Now, because often when you're going to save something is when it'll have to look at everything at once, meaning it finds the problems. So, okay, what should we do? Well, should we just ignore the problem and just keep going? Well, congratulations, you've now just corrupted the old copy of the file. So instead of failing to make an update, you've now destroyed what already was valid. And this is a real problem. This can actually happen. And there's ways to avoid that and reasons why you do so. Now, you want to look at it in the case of, well, can we just handle the error? Well, yes, you can. However, that's not a crash. Now, if you can handle the error, which you should, that's the optimal solution. That means that you know what state you're going into. You know how to handle that kind of invalid input. The thing is, you can't handle these in general. Sometimes you can handle certain classes of errors that are all kind of the same sort of issue, and you know how to sort of, okay, we're going to cut off that kind of decision we were trying to make because we understand that that kind of error is isolated to that kind of logical operation. So we can actually abort what we were doing there and report the error and then continue on. But that's not a crash because you actually handled it. You knew what to do with that input. So in general, avoiding a crash is actually not possible. No amount of policy will make sure that things that are wrong suddenly act correct. That's not the way it works. Even logically, that's not the way things work. Now, also this leads into some problems relating to security. For example, what happens if you failed to verify a login? Now, this isn't the same as, oh, someone didn't log in with the correct password. It could be, for some reason, we failed to really understand what the login meant, because maybe they're trying to break into the system. So they're trying to get past how we normally do things. Well, what do we do if that happens? Like if they get past something in a way we didn't really understand how to work with. Should we just log them in anyway? Well, hopefully not, because they're probably an attacker. Trying to get in would be a problem. Making sure that you actually know how to handle these cases instead of just kind of allow them to slide is important, because doing it wrong, allowing things to slide, remember, this could be someone's definition of just do nothing. So you need to actually a crash would be better in that case. Something like Heartbleed, that fairly recent security problem that we had all across the internet with encryption libraries, this is not exactly the same example of this, but it's a way that you could have said, okay, well, it would have been better if we had crashed instead of leaking out that data. Right? Remember, it was just something that there had been a missed piece of checking in the input that we had received from an untrusted source. And we trusted the data without validating that it was correct and within limits. And so that was how they were able to get additional information. Yes, the right answer is just to handle that check correctly, and that's the change they eventually made to fix it. But this could have been something where, okay, if we could have chosen a crash instead of that security bug, that would have been a better option. And there would have been ways to do that, but still, that's another one of these, hindsight's 2020. So really what it comes down to, and what I'm trying to get at here is, it's better to crash than to pretend that you know what you're doing. Remember, things are either correct or incorrect. There's no sort of correct. That's just a special way of saying wrong, but I'm not acknowledging it. And that's even worse. Putting your head in the sand doesn't fix the bug. So, okay, if we're saying that maybe crashes are preferable to certain kind of unexpected behaviors, is there any way we can actually force them to happen? And would there be a reason to do that? Why would we want to look at things this way? Well, really what we want the program to be able to say is, am I in a valid state? Is the thing that I'm about to do, does it even make sense right now? Are my assumptions correct? That the assumptions of the things I'm about to change by doing something, by implementing an algorithm, are they actually right? Because I don't want to proceed if they're wrong, because that just means I'm going further off the rails. So can we force there to be a check of a valid state? And the answer is, yeah, more or less. Of course, the whole machine state is huge, but if you want to be able to check one thing, you can always assert that it's true. And what this means is the assertion is just a statement of truth. It's just you're saying to the operating system or the underlying library, whatever you're using, I claim this thing is correct. And if it is correct, nothing will happen. You just proceed because it's correct. Your assertion was true. It succeeded. The other case where you say, I claim this to be true, and it's false, that means you've failed your assertion. So what it should do is crash your program. So this can actually cause crashes to happen earlier or more often, however, which sounds like a bad thing. However, paradoxically, this actually helps a lot. So why would you do this, and why is it a good thing? Well, the obvious one is you can find bugs earlier. Right? Instead of finding a bug once it's much, much later in the program, as a result of this mistake, is very, very difficult because it's potentially corrupted many other things over the course of a long run. So now who knows how you got there. Where you crashed, everything looks correct because that's not where the bug is. It's actually potentially days earlier when you were doing something else. The other reason is to prevent security breaches. Again, if something like in that Heartbleed example, just to sort of contrive a way of looking at this, if instead of copying out the data that the attacker had requested, if first the program said, okay, this number I'm about to copy, it's within the range of what we think it is, right? I'm going to assert that that's a reasonable thing. Then instead it would have crashed, instead of actually returning the data, meaning that there would not have been a security breach. It would have been at worst a denial of service attack. But because of the way web servers work, it probably wouldn't have actually caused any problem for anyone. And the other reason is to prevent corruption, right? A classic example of this use, and of assertions in general, is something called a kernel panic. Now, the kernel is the lowest level component of your operating system. It's what interacts with the hardware for you. So it panics if something unexpected happens. And what that means is it crashes you forcefully right away, the entire system. On Windows, an example of this is often seen as a blue screen of death. On macOS, it's that sort of gray window that drops down over the screen saying you have to restart your computer, things like that. And really what this comes down to is, what if you're doing something like, okay, I'm going to go save out this really important file onto the hard drive. And instead of the hard drive returning correct, it just kind of does something unexpected. It gives you some strange error or strange nonsensical response that the software now needs to look at and go, okay, this was not what we expected. This isn't even something I understand. So should we just ignore it and keep going? That probably means we're overwriting other information on the hard drive, or maybe the hard drive's dead, or something like that. we probably just want to crash because we're about to make things probably a lot worse. Right, because what if you're going to proceed? Now you're corrupting the hard drive, maybe? Right? It's hard to tell. So formal verification is a way of looking at what correctness actually means in a mathematical sense. Now, this is actually something that is not realistically done, but it's more something you learn if you take computer science at a university level, how to understand the math behind logical correctness and how to actually be able to prove things. So the idea is, like, it comes down to, can we prove correctness? Can we prove whether an algorithm is correct or not? And how would we do that? And it comes down to a very simple idea that, okay, every algorithm has preconditions and postconditions, things that must be true before it runs, things that must be true after it runs. And based on that, can we prove that whatever is going on between these two things, the before and after, by looking at the code we have, can we prove that if the precondition is correct, this algorithm will always give you a correct postcondition? And in some cases you can. Now this is, of course, an incredibly complicated thing to do. Pretty well never really feasible to do in the real world. And of course there's ways you can get this wrong that make it kind of a moot exercise anyway. So it's something that you don't actually see anyone realistically do, but it is something you learn about if you take this at, say, university level. And it is an interesting idea. There's also cases where not only is it not feasible, it might not even be possible, right? What happens if you've got things like a multi-threaded program where there's, two CPUs on your system are running the program at the same time? Just because you understand the order in which things are happening in one of them doesn't mean you can prove the relative order of how they're happening on the other CPU. So this can cause problems that make it not actually possible to run formal verification. And in general, you don't end up in these situations, but some algorithms do have to worry about this. So that's part of the reason you don't see this happen. The other one being you're more likely to make a mistake than actually get through it. And it is very time consuming to do it. So I hope that's helpful, sort of a quick way of looking at, okay, what a crash is and why it might not be the thing you should be so afraid of, because it might be saving you from something much worse. So again, leave me a comment here if you have any questions relating to this, or send me an email. And of course, if you're using Open Autonomy, you can trust me at this QR code or URL here, and I'll talk to you later. Thanks. Bye.